I need a working clicker. Okay. I hope you understand the cultural reference. And if you don't, they used a very famous composer music by John Williams. And if you don't understand who was the person of reference, then you obviously get a like from me and from the organizers. Still, my presentation is called The Dev Wars, the Exponent Strikes Back. Logically, after this presentation, here in Luzhniki, at the Positive Hack Days, I should have been on the dark side of the force and look like this. You can see it on the screen. Let's have a quick experiment. Do you know at least 4 characters here on the screen? Okay. And who can see who knows 5 people? There are people who know the dark force. You, as you can see, present on the different part of the force. I represent the Republic. I'm also a div elite programmer at Positive Technologies. And obviously, I'm speaking from the light side. I work with the development, optimization, and social analysis vector, which looks for vulnerabilities and helps us, developers, to make the world a little bit better, checking and fixing our vulnerabilities a little bit faster. During this presentation, we will speak about this creature. This is called an exponent. But obviously, we will be speaking about the exponential speed of the exponential speed, and we will be speaking about the real speed of the function. But we will get back to it later. In general, our team has been working for many years, for about 10 years, and works with statistical analysis. You can see how funny, how happy we are when we work with statistical analysis. Moreover, for many years, we've been giving presentations on stat analysis, performance, and you can see how bright we are during our presentation. Still, jokes aside, we are working with statistical analysis, we do give presentations, and this presentation will be a sequel and spin-off of these 2 presentations. Here you can see them on the QR codes. That's why the presentation will not have any introduction, so that we can cover more.
Я, кстати, наверное, забыл представиться. Да, меня зовут Георгий Александреев, кто не в курсе.
By the way, my name is Georgi Alexandrium, just in case I forgot to introduce myself. And let me remind you that we are talking about abstract interpretation. This is the change and transformation of the source code without its implementation to some kind of other entity so that we can get some kind of information from it. So, for example, when we transfer data, when we work with transferring, when we work with semantics, and so on. But formally speaking, abstract interpretation is homomorphism of linear dimension into other linear dimension. When we're talking about the data transfer, then we are talking basically about graphs. If we add, for example, that outer data, arguments, entry points, the requests to databases, to outer services, replies from the outer services, if we consider them unknown factors, potentially harmful, and we mark and tag them as symbolic measures, as symbolic values, they can have anything inside, then we will get symbolic analysis. And you can learn about this using this QR code, so watching and listening to our previous presentations. Next, let us remember a few terminology, a few definitions, so that it will be easier for you to understand me and it will be easier for me to tell you about this. A variant is a pair X and Y, where X is some kind of value and Y is the condition of reaching this kind of value. We define this that Y goes into X. Variative area is all the possible ways of this area. So probably you cannot see this on the back of the screen, but we have a small function which takes in 3 parameters. And you have 3 values inside, 3 x, y, and z. And depending on the values, we put in some values. Then we return the concatenation of 3 variables x, y, and z. During the concatenation process, each of these local variables have variative sets with 2 options. As x, we can take any of 2 possible variants. For y, we can take any of its 2 potential variants, and we can combine it with 2 potential variants with x. As a result, we get 4 potential variants. And for z, we can take 2 potential variants, each can has, and combine it with any combination of x and y. As a result, we get the concatenation of 8 potential alternatives, or 8 potential options. But if we imagine that we didn't have 3 local variables x, y, and z, but n instead, then we can get the n number of variants. At the end will be the multiplication of power n to the power of variative, and it depends on the number of elements. Let's assume that the minimum power of them is k. Then it returns that the number of variants as a function will be at least, and I repeat, at least, as k to the power of n. Skipping a few formalities, we can deduce that our function, the number of variants depending on the variative sets, has a very specific speed, in very special exponential speed. If we assume that k in this set will be equal, let's say, 2.7, at least, very, okay, so let's say k equals to exponent, and then we'll have the exponential growth of the speed. And then during this presentation, we will say that we have the exponential growth of the speed. It's just easier. You know about the exponent, at least from the title of the presentation. I know about the exponent. So it will be easier for us to say that we are talking about exponential growth of the speed. Okay. Please raise your hand if you watched our previous presentations from previous PhDs. Okay, we do have some people here in the audience. During the previous presentations, we considered special cases where formally we proved that the upper bound of the number of variants actually is significantly lower than an exponent. There were cases where I formally proved that this number was a linear value, but unfortunately this was a very specific case. But in general case, unfortunately, exponent still is there. It's a fundamental problem for symbolic analysis. That is why the number of exponents, the number of variants increases very fast, using exponent as a mark of speed. So the question is, what do we do? If we still have to work with exponent, how do we do this? Unfortunately, I will not tell you anything new here. We can either increase the resources or we can change the analysis. Basically, what will you choose? Both of these options are not very good. In terms of resources, we can allocate more RAM, more external memory, increase the properties of a processor, number of processors, but still there are 2 points, 2 caveats. Point number 1, money. Do we have enough money to single out additional resources? Well, suppose we do. Then caveat number 2. In actuality, increasing the resources will not solve the problem of exponent because it just pushes it a little bit. When you have enough resources, you can scan this of your symbolic analysis, but after some changes in your code database, you will still face the fact that you do not have enough resources and you still need more and more resources. in theory, until you have infinite amount of resources. Well, I do doubt that people have infinite number of money and resources. In terms of analysis, we can forego symbolic analysis altogether, and we can go a class below. For example, we can analyze flow data, or we can compare syntactic trees comparison and contrasting, or we can use pattern matching. Obviously, there are benefits. They do not consume a lot of resources, but the trade-off is accuracy. Are you ready to work with lots of false positives, or even worse, trying to look for false negatives? So false positive is when you found something which was not supposed to be found, and false negative is when there was no that was supposed to be found. Because of this, in this presentation, we will be talking about changing the analysis, trying to cut some corners. And I am putting emphasis using only heuristic methods, trying to stay within the symbolic analysis without going to a class below. Within the symbolic analysis, we use two entities: source code and data we get through the analysis of this source code. Because of that, cutting some corners might be possible only for these two entities. And because of that, we will consider the capabilities of decreasing the coverage of symbolic code, data filtration, and data approximation. We will go into details on each of these 3 points. Let us start with the decreasing the coverage of symbolic analysis. In general, we can consider the properties of a code, like its clarity and its importance or lack of importance. So, for example, clear functions are deterministic functions without any additional effects that depend only on the input arguments. And the function is determined. If we pass some input arguments, we get the result, and every time when we give the same argument, we'll always get the same output. And side effects mean that if we have some kind of function that does function A, it will not do something else. It will not add data to a database. It will not show me a notification. It will just do A as it was supposed to do. Let's see an example. This is a function that will return us a squared multiplication number to number. There are no anything else. It just returns a square of the input argument. Now let's assume and see the example of dirty function. In this underlined function, we address some kind of value, some kind of variable which is defined in the outer scope. It's defined in the program, but not in this function. And because of that, we violate determination of the function. Because if we pass the same argument, we will have different outputs. And below, we can see that there is a side effect. We write something somewhere else. And because of that, this function is dirty. Or we can say this is a pure function or impure function. This would be the correct way to refer to them. Now we understand what's impure function and what should and what we could do with this. Now let's take a look at a more interesting example. We have a function which takes in input argument and it does something with this argument. On the first line, we can see that we have an array with about 500 elements from 513 to 1024. Then we iterate through all the elements of the massive of this array. Then we accumulate all the values of this array, and then we multiply it according to the formula on the screen. Then we return the result, which will be the sum of the elements of all the array and multiplication of R multiplied by each element of the array, as you can see on the screen. In the body of the function, we perform quite a lot of different functions and operations. First of all, we have an array for about 500 elements. Second, we did about 2,000 operations of addition and about 500 operations of multiplication. And I'm not I'm talking about additional checks and balances. Obviously, if we do it one time, it's not anything wrong. But if we do it thousands, hundred thousands, millions, and billions of times, the number of operations will be very, very high. That's why we want to decrease the number of operations. And we are talking about the real performance, not just about symbolic analysis. That's why there is a compile.
У нас функция, если вы заметили, чистая.
That's why we use compilers. So this is a pure function. It's not deterministic. It does not have any side effects. That is why we can do as follows. We can use cache, where the key would be a set of input arguments, and the value would be the result of the calculations based on these input arguments because of the work of the function. And every time when we call the function, we will go into cache, check if they have the same values for the argument, and if they are, we will take it from them and we will not compute it. But if they do not have them, we will compute it. So in case we have 5, originally we have cache missed, we'll calculate it, we'll put it there in cache, and during the second try, we will go directly to cache without calculating it. And the same applies to 17 if it was the input argument. Okay, we don't understand the difference between pure and impure when they are working in real life, but how can we use it for a symbolic analysis? Let us remember that we have a lot of different operations, and we were able to decrease the number of these operations thanks to using cache memory. But still, we have to calculate it when we have unique number of arguments, and their number can be infinitely big, depending on the number combination of input arguments. We would want this function to calculate once, and that's all. So maybe we can do this. We will say that we will take this function, we will discard all the external context, and we will analyze it from the symbolic point of view, assuming that input argument can take any values, being obviously an integer. After this symbolic analysis, we will get summarization table, or maybe symbolic template. As a key, it will use some kind of variables, which will be modified during a symbolic analysis. And the values would be some kind of calculated value, which that way depends on the symbolic input arguments. In this specific example, we have the result value, which depends on the input argument, x, which is symbolically unknown. It can take any values which are possible for integer because there are no other limitations. Thus, we get some kind of summarization table. We've analyzed this function only one time. So here's the caveat number one. Once we get the summarization table, we can use the summarization table to run additional compiler optimization. For example, cluster unfolding and cluster propagation. So once we pre-calculate all possible values, which can be there.
Вот. Второе, что мы получили,
Next point,
у нас есть таблица суммаризации, которая говорит,
we have this summarization table, and it tells us that the variable changes inside and it depends on the input argument. So how can we use this? Every time when analyzing other functions, and we can see that there is a call of this function, we can take arguments, we can take these values, and we can look for the arguments in the summarization function, summarization table rather, and then we put those arguments in that table. So instead of calculating and running the whole function, we just look for it in the memory cache. By doing so, we are able to cut a lot on the number of operations. But I remind you that we are looking for heuristic approaches, and there are always caveats. There are several things connected with this approach. The main one is that the definition of purity of a function. In most cases, web applications, mobile applications, desktop ones, which are being developed right now, they use object-oriented programming languages or structural paradigm, imperative paradigm, and so on. And who really knows that
Мы можем
there are not
начать
so many
применять данный
pure functions in
метод,
those. We
получим
can
какой-то
use
профит.
this kind of
Этот
heuristic to
профит
them.
не
We will get some
соизмерим
kind
с
of profit,
количеством
but this
трудозатрат,
profit
необходимых для вот этой
cannot be
реализации. По этой
justified
причине
by
хочется
the
каким-то образом
amount of resources we would
расширить
use to
определение
get it.
чистых функций.
That is why we want to, let's
Так вот,
say,
мы будем считать, что у нас
expand the definition of
линейная
pure function.
функция,
We will consider
которая
that
зависит только от
deterministic
входных
function that
аргументов
will depend
и
on the input
зависящая
arguments
от состояния
and depends
памяти
on the
виртуальной
state of
машины, но все так
memory
же
of the
имеющих
virtual
точность элементов,
machine.
будет
It does
называться
not have any side
расширенной
effects,
чистой
but
функцией.
then it will be
Давайте мы
called an
сейчас за
extended
пример
pure
грязной нашей
function.
функции, которая была в
So
начале,
let's
попытаемся сделать
change our
расширенную
impure
чистую функцию.
function into
Ну, для
extended
начала
pure
составим условие.
function. First of
Мы
all,
уберем побочный эффект.
we will
Просто выкинем, у нас его не будет.
remove this
Дальше мы
side
смотрим,
effect.
что
We
у
will
нас
remove
есть
right.
обращение к
Then we
переменной,
can see that
которая
it
находится вне
refers
скопа этой
to a
функции.
variable which is
Для
outside the
этого,
scope of
чтобы
this
убрать
function.
недетерминированность,
In
мы
order to
введем
remove this
новый неявный
non-deterministic
параметр,
thing, we
который
will
будет называться
add
symbolic virtual
a
machine state,
new
то есть состояние
parameter which
памяти
will be
виртуальной машины.
symbol SFMS,
И все
symbolic
обращения
virtual machine
к
state,
переменным, которые определены
and all
вне
the
рамках этой функции,
calls of this function,
мы
which will
сведем
be
к
outside
обращениям
the
к этой
scope of this
переменной.
function,
Эта
will be
переменная на
referring to
самом
this
деле во
variable.
всех
And
вызовах
this
этой функции
variable, during
будет
all
в
the
себя
calls of the
принимать
function,
снапшот
will take
памяти
in a
виртуальной
snapshot
машины.
of memory of
Иными
the virtual
словами, мы
machine.
переадресовали
So, in other
вызовы во
words,
внешнюю
we
память текущего
readdressed
состояния
the
в
calls to
некоторый
the external
снапшот,
memory to
приготовленный
some kind of
виртуальной
snapshot
машины,
for the
который всегда будет
pre-prepared
передаваться по
memory,
вызове этой
which will
функции.
always be sent
Таким
there
образом, мы
once this
расширили
function is
класс чистых
called.
функций,
By doing so, we
увеличили
are able
частоту
to
срабатывания этой
expand the
эвристики.
class
Но
of
понятное
pure
дело, что тут тоже есть свои подвохи, которые, если кто
of
захочет,
the
мы
pure
сможем
function, but
обсудить
obviously
точно в
there are
кулуарах.
some problems, and if you want to discuss it, we can do it later
Итак,
after the
поговорим про
presentation.
значимость и
Now,
незначимость
let
функций.
us
На самом
discuss
деле, так как мы
importance
занимаемся
or lack of
символьным анализом
importance of
и
different
ищем
functions.
уязвимости,
Since
далеко
we
не
are
все функции
working
для нас
with
важны.
symbolic
Мы
analysis,
хотим
not
анализировать
all
только те
functions
функции,
are important.
которые,
We want to
во-первых,
analyze only those
приводят
functions
к
that,
обращению
first
к
of all,
внешним
bring
источникам данных,
about
или
the
же они
referral to
приводят
the
к обращению
external
к базам
sources of
знаний.
data,
База
or they
знаний — это
refer
такая
to the knowledge databases.
солянка различных
Well, knowledge
правил,
databases
всего
are
прочего,
basically a
которые
compilation of different
созданы
rules and
анализатором для
requirements
того, чтобы можно
which
было
are
делать
there
какие-то
for
сопоставления с
analyzers so that you
поиском
can
уязвимостей
compare and
в
contrast
помещении.
different
Так вот,
vulnerabilities and so
если
on.
оба
So,
этих постулата
if both
нарушаются,
of those
формально
rules are
говоря,
violated,
функция для нас
then formally
незначима.
the
И мы
function
можем
is
отбросить ее
not
при анализе,
important for
не
us,
анализировать
and we
полностью.
can discard it
Давайте
and
на простом примере посмотрим, что это из
skip
себя представляет.
analysis at all. So let
Есть у нас
us
функция,
look
принимающая
at
два
a simple
параметра
example.
и что-то
We
делающая.
have a
Получающая
simple function
значение,
which
записывающая
takes
свой
in
память
two
в тест.
parameters
Если
and gives some
посмотрим,
kind of
мы
output.
нигде не обращаемся к внешним источникам
We
данных,
do not
где
refer
могут
to the
содержаться
external sources of data,
данные, которые злоумышленники
which
передали,
could have some
чтобы
data
скомпрометировать нашу
passed
приложение.
by
А
malicious
также
users
мы
to
нигде
compromise
не
our application.
обращаемся к
And
опасным
we
операциям,
never
которые могут
refer to
привести к тем
dangerous
самым
operations
уязвимостям.
which could refer
Поэтому данную
or
функцию мы
incur
можем вообще
vulnerabilities.
символикально анализировать.
So we don't have to
Независимо.
symbolically analyze this
Если мы
function.
посмотрим,
But
функция возвращает
here's a
какое-то
catch.
значение.
If we can see at this
Во-вторых,
function, it
функция
returns some
пишет
kind of
что-то
value.
во
Then
внешнюю
it
память.
writes something to the external memory.
Мы в рамках символьного анализа
Within
должны
symbolic analysis,
предполагать, что
we
после
have to
всякого
assume
вызова такой
that
функции мы
after calling
получили
this
какой-то
function,
результат,
we
и что
will
в эту
get some
переменную
kind of
записалось
result,
какое-то
and
значение.
that
Мы
this
не можем
variable
это
would have some
проигнорировать по
kind of
той
value.
причине, что
We
если мы
cannot
это
ignore
сделаем,
this, because
то
if we
можем
ignore,
получить false
we
negative result,
might
что
get
самое
a
плохое.
false negative,
По этой
which is the
причине,
worst case scenario.
построив таблицу саммаризации при первом анализе,
Once we
как мы
have the
делали для чистых
summarization
функций,
table,
мы определяем,
as we did for
какие
the pure
переменные
function,
нам нужно
here we
запомнить,
can define what
ну,
kind of
интерпретирующие значения
valuables
или
we need.
внешние переменные,
The
и затем всякий раз при вызове этой функции мы ее не
And when calling
анализируем.
this
Мы
function,
берем
we will not
таблицу
analyze this. We will take the
находим эти
summarization
переменные,
table,
и во
look
все
for
эти
these
переменные
variables,
мы
and for
записываем
all these
символьное
variables, we will
неизвестное,
state
которое может
its
принимать любое
symbolic
значение.
unknown, which can
Тем самым
take
мы
any value.
уменьшили количество
By doing
выполняемых
so, we were
операций,
able to decrease
но
the number
добавили
of
некоторую неточность,
operations,
символьную
but we
неизвестность.
also add some
На этом я вас
ambiguity,
поздравляю.
symbolic.
Половина доклада позади. Да, спасибо за аплодисменты.
Now the half of the presentation
Дальше мы с вами...
is behind us.
Дальше мы с
Thank
вами
you for the
поговорим про
applause.
фильтрацию данных.
Now
Под
we will
ней
talk
мы
about
подразумеваем
data
уменьшение
filtration.
объема данных, которые мы
Data
получаем
filtration
при
is
символьном
the
анализе
decrease
за счет
of the volume of
выбрасывания
data
ненужных или лишних.
by or
Давайте на
through
примере посмотрим,
discarding
что это
unnecessary
такое.
data.
Есть
So let
функция,
us look at an
которая принимает
example.
один аргумент.
There is a
Во-первых,
function which takes in one parameter. Based on its value, it might return some kind of string in font, large, huge, small, and so on. In this case, we have a variative set, which consists of 6 possible variants. Suppose we have an understanding of the business logic of an application, and we know that users oftentimes use this function without passing some value that would be more than 2 to the power 16. So we can remove the last variant because it contradicts this business logic of the application. Okay, we decreased the number of possible variants. But using the same business logic, we do know that users really do not want to use this kind of function. And the maximum they can do is 2 to the power of 8. Then we can remove even 2 possible variants. So we removed the volume of data. And we can speak about data approximation here too, using the same example so that we will see how it's used there. So data approximation is decreasing the volume of data through replacing data with the other set, which obviously is lower in size. So the same example, suppose we know that according to the business logic, script size and floating size is pretty low, just 1% when people use these two variants. We don't really care how much, we just know it's low. Instead of 2, we can just use one of them. So instead of 2 of these variants, we can use one of them, but changing its conditions. And suppose that users do not really want to use very big font because it's too screamy. That's why the 2 biggest fonts are not really used, maybe 0.005. That's why we can change and use only one of them, and obviously change the conditions. Once we approximate, which is based on the business logic, from the 6 possible variants, we get 4 possible variants by changing the volume of data. I can see your question. So what's the reason? What's the point? Well, there is no point. There is no reason. There is no difference between data filtration and data approximation. If we use data approximation as a function, which image has a null set. And this is the reason why later we will assume that we are talking about data approximation. Basically, because data approximation and data filtration is basically the same at this point. Okay, so we understand how data approximation works, but now we need criteria when we can run this approximation to decrease the volume of data. That's why in our examples, we used some business logic. But unfortunately, the business logic for different applications is a separate set of problems and work. That is why we are not considering these criteria during this presentation. So instead, we need criteria that would allow us to work with what we need. So code semantics, which is based on the source code, and the data which we get through this symbolic analysis. But in order to do so, we have to understand what we are working with when we analyze the source code. Abstract statistical tree is an oriented marked tree with the nodes being operators and leaves are operands. So here's a simple example with a number of different operations, addition, multiplication, and we'll get the statistical tree. Here's how it will look like on the right. As you can see in the nodes, we have operates, and on the leaves, we have operands. And you can see that there are no brackets here because we are going around this tree. The abstract tree does not have any information about the syntaxes. If we have any comments, any line transfers, it will not have any of these. And that is why abstract statistical symbolic rather tree is more stable to the grammar compared to the other tree. And this is what we get when analyzing the source code. All analyzers get this kind of source code image. And we will use this tree, assuming that our application will use this structure. And now we finally are getting crazy.
Не переживайте, я вас проведу.
But we will use linear speed, so don't worry.
По той причине, что в
And the reason for us to go crazy is that at some point we will have an analog of multi-measure KD trees, which we'll try to represent as 2D dimension. And we'll try to explain what I mean. We do understand what it means to have an abstract semantic tree. And now we want to have the first criterion. Well, obviously it's a tree, it has nodes. Let us consider the number of trees, or rather consider and count the number of nodes. And we will call it a structural complexity. So we have some kind of...
У них, в свою очередь, все так же могут быть свои подвыражения. А у них рекуррентно и так далее.
We have some kind of expression, and those expressions could have sub-expressions. And at this point, we want to understand how many expressions our root element has, the element G on the slide. Well, it's simple. Let us count. Let us count the expressions. Structural complexity for the expression is 1 if the expression does not have any sub-expressions.
Вариативного множества равняется максимуму структурных сложностей значений вариантов этого.
Structural complexity is maximum if it has a variative structure. And when we're considering sub-expression, it will be the addition, it will be sum of different sub-expressions. So based on these three expressions, we can get the complexity based on these three formulas on the screen. Now we can calculate the number of nodes on the tree, but we are talking about symbolic analysis. We have variants, we have options, we have different branches. And it can turn out that we do not have a lot of nodes, but lots of variants. So we want to understand how many variants an expression could have. Let's call it meaningful complexity. Here is a simple example. The input expression has n number of expressions, of sub-expressions. Since this is symbolic analysis, some of them could have variations. Variation expressions could have different expressions in them. And those expressions could have sub-expressions too. Since this is a symbolic analysis, then new expressions could have their own sub-expressions and subsets, and so on, and we get more and more recurrent that there is recurrence, that there are some expressions have sub-expressions and sub-expressions, so the sub-expressions have even more sub-expressions. And now we want to understand how many alternative variants we have for our element G if we consider each of them at a certain point in time. So I will give you the formula right away here on the screen. The meaningful complexity is 1 if the expression does not have any sub-expressions. There are no alternatives, then the complexity will be 1. The complexity would be the sum of meaningful complexity if there are multiple sub-expressions. And number 3 would be the multiplication of these sub-expressions. It seems good. We calculated the number of nodes, we calculated the potential variance, but let's take a closer look at the picture. You can see here on the slide that we forgot something. Variative sets have variants, and variants have values, but also conditions. And as you can see in this semantic tree, we do not consider conditions anywhere. Now we have the third criterion, which is called conditional complexity. This would be the maximum number of potential conditions for all the expressions and sub-expressions. Now let us see what and how it would look like. We need only this part of an example. We have a variative expression, a variative set rather, and we remember that we have different conditions. Those conditions could have some sub-expressions. Those sub-expressions, since we're talking about symbolic expression, could be variative sets. And those variative sets could have conditions and expressions with conditions and without conditions with some values. Both could have their own sub-expressions and so on and so on. And then we have this recurrent condition that an expression has a sub-expression that could be a variative set. Those variative sets could have conditions and values for different variants, which could also be expressions with their own expressions and sub-expressions, and it goes on and on. If we take a look at the original tree, it will be the representation of the values against the trees. Once we get from the value to the condition, formally we created a new dimension. And in this dimension, we made the condition as the root cause, and we started building the tree from this condition. Basically, we get two dimensions. If we take a look at the second dimension, and then we would create the third if we had a different subcondition in one of the sub-expressions, and this would go on and on. This is the analog of multi-dimensional KD trees. So this is the formula on the screen. We consider that conditional complexity equals to 1 if there are no variations. And then we are talking about variative sets. It will be the sum of multiplication of conditions and values of variance from those sub-expressions. And finally, point number 3, we have the multiplication of conditional expressions for sub-expressions of that variant. You can see the formula on the screen. Now we have 3 different criteria, and we finally have to come up with an approximating function, which will take those 3 criteria, and we will get something as a result. So what kind of function should do this? It should be an approximating function. It should decrease the volume of data, otherwise it doesn't work. Second, we are working with symbolic analysis to look for threats and vulnerabilities in the code. So we need to remain and retain some qualities. Qualities and attributes. We want to maintain that there were some references to external sources that malicious users potentially wanted to transfer some data. And we also wanted to maintain that there were synthesizing functions like HTML code, URL code. We need to understand that these data were safe. And third, we want to maintain the type of the expression, if it's present. We do not want to work with a string and then work with something else after approximation. Okay, now here is the approximation function, which produces a new symbolic unknown value, which we call the sealed value. It sets all the values equal to 1 and accumulates all the properties and all the conditions which were mentioned during the previous slide. So this is the approximating function which we use. In other words, what we did is, within the symbolic analysis, we had some kind of tree, some kind of abstract big tree. We took a part, a sub-tree, and we removed it, removing all the values, all the conditions, and replaced it with one single expression. And we said that the complexity is 1, and we accumulated all the conditions. And we marked it as a symbolic unknown because it takes all possible values. By doing so, in terms of symbolic analysis, we were able to have some measure of we're able to have some kind of values, and I do understand that you would want to see some results for heuristics, but you do understand that it's impossible to do it within 1 hour. So let us take a look at one of the examples and see what we give as a result. Here on the slide, you can see that we had different tests when we took the meaningful complexity and decreased it from 2 to the power 16, from 2 to the power of 16 to 2 to the power of 8. And you can see the changes which happened during the scan. On the green, you can see the good changes, but orange are not so good. Let's consider the first example, hap Node.js. after decreasing the limit of meaningful complexity, now we do not have to reach the limit of allocated memory. The scanning didn't stop as often because we had enough memory. And because of stopping memory scan less often, we were able to analyze more code. And that's why we decreased the memory limit and increased the time. And the fourth example, we can see that we have decreased the time it takes to analyze. We decreased the number of variants, and as a result, we decreased the memory consumption. But at the same time, the number of threats also decreased because approximation removed a number of alternative branches, and we were not able to get the threats from that area. We get only the general idea. And clearly, all those are heuristic approaches. They have benefits and they have their own drawbacks. And there could be some fringe examples where heuristic worked really, really well, or maybe it was pretty bad. Maybe scanning became even significantly slower. And this is the end of my presentation. Well, I would like to say so, but there are a few moments which we still need to discuss. Within this presentation, we still need to consider how these complexities and approximations are connected to our previous presentations. In general, we considered three potential ways to calculate complexities. We did not cover cutting corners when analyzing dictionaries, arrays, collections, and so on. We did not cover the banes of symbolic analysis, arrays, and recursions. And this is a big problem there. Moreover, we didn't cover approximation of code. When we take the source code, we simplify it somehow, and then they analyze the new way, the new source code, just to decrease the number of operations, and many, many more. I do understand that within a single presentation, it is impossible to cover all these aspects, but I hope you know what I mean by saying this. If you understand that you are into graphs, into algorithms with graphs, that you care about optimization of algorithms, or you care about grammar languages, you are not afraid of INTL, LFBM, or you know that there are some problems both in. If you are really good in JavaScript, or maybe you know about the canary of security, then you can leave your vacancies here. We are looking for researchers and developers in source code analysts and threat analysis. To sum it up, I would say that I tried, and I hope you will use this link and you can analyze and give me some kind of feedback, but also answer a number of questions from the organizers on these tracks. That's all I wanted to say. Thank you for your attention. Georgi, thank you for your presentation. I think it was very, very good. Dear colleagues, let us give a round of applause to Georgi once again. Let us evaluate, give the mark to this presentation. First of all, you have to give this mark, this presentation. And to do so, you need to download our bot. Now I would like to ask Ivan, who is in charge of questions from the audience. So, what are the questions? I do have a few questions. Question from Dmitry. Recursive function is this a pure function or not? At the end, we said that we did not analyze the analysis of recursive functions, so we did not consider it during this presentation. Here is some inside information. We have a heuristic for this, so you should wait for the next presentation. Okay, thank you. And question number 2 from SCV. How data are processed, which they get from the external block? Well, it's simple. They are considered non-trustworthy data, which can consider some potential malware, and they are considered with symbolic unknowns, which can take any values. But initially, within the specified type, unless there are additional conditions, once there are additional conditions, you can decrease the potential values of these variables, and that's all. Okay, thank you. We have 2 questions. Maybe if there are any more questions, please send them. Be very specific. I have a question too. We are waiting for the next presentation. It seems like you're trying to create some kind of big drama, big saga consisting of multiple parts. Okay, so please select the better question of these 2. I think it's even harder if you had 10 questions to select from. I have a question. So we are talking about linear dimension, but what kind of operations happen in this linear dimension? I think this is a very good question, and we will answer this later, just not to take away time from answering the question. But actually, it should have 2 operations at the same time. Thank you for the presentation. My question is, during the first optimization, I think if we have a pure function, we will change the result to symbolic value. We will have the resume of this function. And in the example, it was quite beautiful because it had iterations on arrays, but the number of arrays has a fixed number of elements. So the question about the expression of this value. What would happen if the number of iterations dependent on the x, on the input data? Because if we have just arithmetic expression, I can understand how it would look like x plus 3 multiplied by 5. But if we do have an unknown number of addition elements, what would happen? Thank you for the question. It's a very good question. First of all, this is a question to how do we process recursion. We have our own heuristic, which we didn't cover in this presentation. So the answer is simple. Listen or wait for the next presentation, or you can catch me later. We can discuss it later. My question is, we put the function, well, we analyze the function, we understand that it's too complex, we say we do not want to analyze this, and we approximate it. If I understand it correctly, then we approximate the function completely. Did you try to approximate a part of this function so that you could maintain the logic of this function, and then we would have a more precise analysis, and maybe you tried to do so? Yes, we tried. Within the presentation, I didn't mention that the class of extended pure function is only partially extended because you can actually extend it more and more. But within the presentation, it was not considered. If we say about the results, then not always we understand the profit of calculating the narrowing of the function and what's not considered. Grigory, it's very interesting when you're talking about that you should wait for the next presentation to hear about the answer. I have a question regarding the function with array. Why was it 512 divided by 2? Well, it's a sum of arithmetic progression. Okay, and the next question, in the analysis, do you consider the vectorization of the process? The vectorization happens when we really happen this. No, what I mean is that there could be some nuances and some side effects from the vectorization. Yes, if we analyze the pure function, we take into account considering the language, but not about the processor processing, because if we consider this, then the dependencies on one processor, on different processors, would be different. So the same function would be pure or impure on different processors. So statistical analyzers do not allow to look for vulnerabilities which are based on hardware. Answer, yes, probably so, because we would have too many conditions in order to understand if there is a vulnerability based on hardware or not. Question? Okay. How do we bypass this? Now we do understand. That's a very good answer. My question is, if summarization of the expression after we get through the first round of the function is multi-dimensional graph, and the same multi-dimensional graph basically is the set of the parameters. Maybe is there some profit in this kind of summarization? It would be sometimes easier to interpret it from scratch. The answer is simple, it depends, and that's why in our team we cannot approve what kind of functions we treat as pure, what kind of functions we treat as impure, because depending on what we pass through these functions, the results and outputs can be very different. Ivan, we do have more questions. Question from V. Is it clear what's below symbolic, but what's above symbolic? I think basically brute force is the higher class compared to the symbolic analysis.
Да, я думаю, еще пару вопросов можно взять. Успеваем.
We can ask a few questions. Question from Andrei. Did you consider supercompilation for code simplification before the analysis? Well, basically, this is what we did. We coded this code propagation. We basically use this. Formally, yes. The answer is yes.
Ты отвечай, я просто говорю, да.
Ага, спасибо большое за доклад. Три маленьких вопроса. Первый.
I have a few questions. On slide number 12, you had three values of input target, 10, 43, and 92. Are those empirical values, so just random numbers? No, those empirical values. Question number 2, regarding the slide 88, you had an expression, the multiplication of meaningful subsets. But what happens if one of the subsets will be equal to 0?
Можно слайды вывести, потому что вот 88 я наизусть не помню.
I don't remember slide 88 by heart, so we have to get back to it. It was the expression number 3 when we are talking about the multiplication, but if one of the elements equals to 0, everything will be equals to 0, so what will be the result?
Да, самое нижнее. Ну, а как может быть сложность равняться
The bottom one. Well, how a complexity can be equal to 0? So basically,
сложность равняется единице.
it will be equal to 1. Yes.
Третий вопрос. Да, 91.
And question number 3, slide number 91.
Есть ли какая-то корреляция? Потому что мы порезали, по сути,
There is some kind of correlation because we decreased the complexity to the power of 8, but the profit was not that big. Well, if we take a look at the third example, we decreased it by from 515 to, well, we basically decreased by a square and decreased time by 70%, and there was no side effects, no loss in vulnerability, no false positives, no false negatives. So depending on the project, heuristics can be either good or mid, which happens in most cases, or very bad in some specific cases too. And I believe this is the time for the last question.
Там был первый человек в очереди. Я слежу за этим. Да.
Не ломай пайплайн.
Хорошо. А, еще у вас вопросы есть?
Да. Коллеги, давайте
We
мы
do
возьмем
have a
еще
few
два вопроса
questions,
коротеньких, потому что
and we
чтобы быть
can
тайминг.
accept only 2 questions just to stay within the time frame.
Привет, спасибо большое за доклад. Вопрос такой, когда мы рассматривали
Thank you for the presentation. When we considered extended pure function, we assumed that the whole impurity would be in the context as a snippet of a virtual machine, in the memory of the virtual machine. So the question is, how do you work with this snippet? In terms of cache, for example, you have to compare this if it's within the cache, but it's big.
Вопрос очень хороший. Это как раз
It's hard to compare.
Нюанс этой эвристики, что
Well,
нам нужно
this
будет
is a
в
nuance of this
формуляризации
heuristic
уметь
that in
сравнивать
the table of
состояние
summarization
виртуального
we have to be
потому
able
что мы
to
считаем
compare
состояние именно отдельным периментом.
based
А что
on
такое сравнить
equality.
состояние виртуальной памяти?
But
Это
what
взять
does it mean
одну память,
to
взять вторую память
consider
и понять,
one
что там
memory
и
with
там
the other
одинаковые
memory?
переменные и
Well,
одинаковые
you have to
значения. Да,
understand
это
that
не
in
быстрый
different
процесс.
memory, these are the same values. And yes, this process takes time. And the last question from Max. Thank you for the presentation. It was very interesting to listen to it. How do you solve the second line problem where you have 26%
Все-таки
of
просто. У нас
vulnerabilities?
просто есть
Well,
дефолтное значение
we
всех
have a
наших
default
которые
value
мы
of
долго,
all our
упорно нашей команды выискивали,
complexities where we
прогоняли,
were
вычисляли и
looking
так далее.
for
И там мы
calculating
исследовательскую информацию.
by the
Это
efforts
2
of
в
our
16.
team.
То есть мы считаем,
And
что это то
here
значение,
it's
когда
2 to the power
количество
16.
не очень
We
хороших
believe
кейсов
that
довольно
the number
мало, с
of
которым мы можем
quite
смириться.
bad
Соответственно,
cases
2 в 8 это
which we
ниже
can
нашего
accept,
дефолтного порога, и мы
but
зачастую
2 to
его
the
не
point of
используем. Просто
2
в
to the
рамках
power of
доклада, чтобы
8 is
показать,
below
что
our
произойдет,
threshold.
были
Usually
показаны
we
именно
don't
такие
use this.
значения.
And we just wanted to demonstrate
У
this
вас есть еще
with
вопросы,
different
что ли?
values.